Recording now. Okay, so linear systems theory. So again, as this course deals with the theory behind time-varying linear systems, and I'm going to define exactly what we mean by linear systems. In general, systems in the world are nonlinear, but we tend sometimes to linearize nonlinear systems because of convenience, because we have developed over the years, humans have developed over the years what I can say a mature theory that can analyze these types of models, and we can also predict how they behave over time, and also design control systems to change their behavior. So this is the main objective of the course. This course is going to be different than applied linear systems. I think the code is ME554. In applied linear systems, that course will cover the tools needed to design controllers for linear systems. And it's mostly focused on time invariant linear systems, which are systems that do not change over time. The model of the system is assumed to be fixed over time. In this course, we are going to consider time varying and time invariant linear systems. And if we have time towards the end of the course, we are going to study a little bit how to design controllers for these types of systems. So this is one the first main difference between the courses. So that course is more geared towards studying tools to design control systems. This course, we are more concerned of how to analyze, predict the behavior of both time varying and time invariant systems. And the second difference is that this course is more of a more theoretical than the other one, if I can say so. Meaning that we will deal with theorems and proofs more frequently. And this practice hopefully will make it easier for you guys to read research papers and write research papers. So this is just a quick introduction. So let's go over the syllabus. So we are going to meet every Tuesday and Thursday from 11 till 12:15. Office hours are going to be Monday, Wednesday, Friday. I think I need to change this. On Wednesday, we are going to meet. I'm going to be available from 4 to 5, not 3 to 4. But Monday, Friday, I'll be available from 3 to 4. The Zoom link is in Canvas. Or you can send me an email to this email at boker@vt.edu at any time, so that we can meet at any mutually convenient time. All right, so in addition to covering time varying and time invariant systems, we will also cover stability, controllability, observability, realizability for these types of systems. Yeah, so this is the objective of the course. The prerequisite for this course is familiarity with matrix and vector analysis, transfer functions, state space representation, which are covered in the undergraduate courses related to algebra and control systems. Math 5524, which is matrix theory, is highly recommended as a co-requisite, but not required. Also Math 4225, which is elementary real analysis, is also recommended as a prereq or as a co-req. The textbook for the course is Linear Systems Theory by Rogue, second edition. I'm going to follow closely this book. There is also another book that I might refer to from time to time, which is Linear Systems Primer by Ansaklis and Mikkel. I believe this book, Linear Systems Theory, is available as an electronic copy from the library. This one, I'm not sure if it's available as an electronic book or not, but I believe also there is maybe a copy to borrow from the library for this book too. Grading, we'll have 2 exams and a set of homeworks. Homeworks, I'll try to make them weekly homeworks. But we will see. It depends on how much we go, how much we cover as we go. The exams, one is going to be approximately in the middle of the semester, and the other one is in the time of the final exam. Exam 2 is not going to be a final, meaning that so these 2 exams, each exam will cover the lectures that precede that exam. So meaning that I'll try to divide the course into 2 parts. Exam 1 will cover the first part, and exam 2 will cover the second part of the course. For the homeworks and exams, it's highly recommended that you type your answers. You can use Word or LaTeX to type your answers. If you don't do that, if you handwrite your answers, that will be acceptable, but probably you will lose few marks. Okay, so I highly recommend, guys, that you type your answers. The exams are going to be take-home exams, and typically I give 24 hours to do the exam. If you have a special need or accommodation, you can always send me an email, and then we'll work together to make it easy for you. So this is the lecture plan. It's a tentative one. We'll start by reviewing some relevant mathematics, matrix analysis, vector and matrix calculus, and this is one of the also maybe objectives of the course, which is to give you guys a heavy dose of matrix and linear algebra, so that hopefully by the end of this course you will come out as a stronger come out with a stronger background and base of matrix and linear algebra. I also gave you I posted a background material on matrix and linear algebra. I hope that you have read it. If you have not done so, please do so this week, because you would need knowledge of matrix and linear algebra throughout this course. It's very important. We'll also cover state space representation of systems, existence and uniqueness of solutions to state space systems, transition matrix properties, and specialization to time invariant and periodic cases. We'll also cover internal stability, Lyapunov stability and other stability criteria for linear systems. Also, we'll cover the controllability and observability concepts for linear systems, realizability, and we'll also dig deeper into the stability notion of systems. And then towards the end of the course, we will cover controller and observer forms, and also linear feedback and state observation. Any questions so far? You can chime in, or you can write in the chat box if you have any questions. All right, sounds good.
I have a question, Professor.
Sure.
So you mentioned you're recording these lectures. Does that mean there's an asynchronous option for this class?
Yes. Yes,
okay,
there is. Yes. So the lectures will be available hopefully automatically. I'm not sure this semester. The Zoom setting is a little bit different than last semester, so I'm not sure how the lectures will be posted in Canvas, but they will be posted in Canvas sometime after the lecture. It might take maybe some hours to be posted, but they will be posted. Yeah, so lectures will be available after the lecture, which means that if you cannot attend, I would like you all to attend live, at the same time as the time of the lecture. But if there is any, if you cannot do that, that would be okay. And also, guys, I highly encourage you to interact with me, ask me questions, interrupt me. I would love that. Please do so. And this is one of the benefits of you attending live lectures, is that you would get the chance to ask me questions, and that would make the lectures more live and interactive. So please do so. Okay, I have a question here in the chat box. Do you give MATLAB homework? So the use of MATLAB is optional. I don't know if I would specifically, I'm not sure. There might be a case where I specifically say that you need to solve this question through MATLAB, but you would need MATLAB, that's for sure. You would need MATLAB that would make it easier for you to solve the questions throughout the course. So MATLAB is needed, yes. I will drop regarding the grading policy, I will drop the lowest homework grade. All right, so that's for the homework. Any other question? All right, let me now stop sharing here. And so I'm going to use a camera capture for the course, which means that I will, sometimes I will use PowerPoint presentations to give the lectures, but most of the times I will be writing. Let me know if this is clear for all of you. Is this clear? Linear systems theory, can you see it?
Yes.
Okay, great. Okay, I need to make people. Okay, great. All right, so I'll start by introduction. Okay, let me see if I make it more lighter here. No, it's not going to. How about this, like that? Is it more clearer now? Okay, just give me 1 second. I'll make sure that I get the best. This is not good. I believe this is the best I can do. All right. Okay. So let me start by an introduction. So in many engineering systems and linear time invariant systems are modeled through different forms. So in what's coming now, I'm going to review how we model linear systems. So in many areas of engineering, linear time invariant systems known as linear time. We are going sometimes to refer to them as LTI, linear time invariant systems. So linear time invariant systems are used as models of physical processes. Okay. I'm going to post these lecture notes, by the way, in Canvas. So if you don't want to write with me, that's fine too. Okay, so so consider the case of unilateral scalar input. So single input, single output systems, and output, scalar input and output signals. Okay, so we will refer to the input as U of t and the output as Y of t. Okay.
Professor,
Yeah.
what does that say? Consider is that the rate of unilateral scalar input?
So consider so consider the case. So
okay.
consider the case of unilateral scalar input and output signals, U of t and Y of t. So meaning that let's consider single input, single output systems, okay? And signals in general that are, so I'm just setting up what's coming now. So I'm just saying to you guys that consider the case of single input, single output, and in general signals that are defined for t larger than or equal to 0. Okay. Linear systems can be represented as, okay, so these are the different ways we can represent linear systems. And so the first one, actually, let me start by asking you guys, how can we represent linear systems? What are the ways to represent linear systems? And by representing linear systems, I mean, how can we, can you tell me of a way to find a relationship between the input and output? Give me an example. Anybody?
So it can be as simple as your output being a linear function of your inputs with respect to time?
What do we call that? Can we call that a transfer function?
Yeah, you can, like, yeah, you can call it as a transfer function. Yeah, definitely.
Okay. Is there, okay, this is one. So is there any other example? What's another way of relating an input to an output of a linear system? Anybody?
A state space representation.
Yes, state space representation. This is second. What's the third one?
Impulse response.
Yes, and also known as what? The impulse response. We call it another way, another term. There's another term for naming the impulse response. It's the convolution. It's called
Convolution, yeah,
convolution representation. There is another one which is related to the state space representation. It's the differential equation representation. Okay, so you define the relationship through a differential equation. So the first one is convolution. All right. So convolution. So for example, here y of t, not for example, this is the definition, from 0 to t. All right. H of tau, u t minus tau, d tau. All right, where h of tau is what? Is the impulse response of the system. So this is really a powerful relationship here. This relationship is very powerful because this tells you that if you know the impulse response of any system, all right, then you would know that, then for any given input, you know the output. Okay, so all you need to know about the linear system is its impulse response. Okay, so here where h of I can call it t here, tau is we call it a dummy variable here. Okay, so tau in this case here is just a dummy variable, but okay, h of t is the impulse response. All right. And it's a real function. Okay, so this is number one. Two is, as we mentioned, the transfer function. So transfer function representation. So transfer function representation here.
Excuse me, sir.
Can you please, all of you, make sure that you mute yourself unless you want to ask a question?
Be h of t or h of tau, the previous equation.
So, Baron, can you ask
Excuse
your
me,
question
sir.
again?
I had a question.
Yes, go ahead.
So I just wanted to ask if it's supposed to be h of tau or h of t in the convolution where you have written where h of t is the impulse response.
Can you see that? Can you ask your question again, please?
Is it supposed to be h of tau?
Yes, h of tau here.
In the next line where you have written it.
Yeah, this is what I'm saying. I'm saying that h of tau is a dummy variable.
Okay.
In general, h of t, h of tau, h of q, whatever. Okay, it's just
Okay.
t. And t here is the time. So
Oh,
where
yes, sir.
h, yeah. So where h of t is the impulse response.
Okay, I got you.
Tau
Thank you.
here is the dummy variable for the integration.
Yes,
Yeah.
got you. Thank you, sir.
Okay, no problem. So transfer function here. So of course, when we talk about transfer function, we talk about Laplace transform or Laplace domain or the S domain. So y of s is equal to h of s u of s. Okay. So where S is equal to J omega, right? And so this is, we live in the Laplace domain or the S domain, right? Where Y of S, H of S, and U of S are respectively the unilateral, Laplace transforms of Y of t, H of t, and H of t here is the impulse response, and U of t. All right. Here, of course, H of S can be a complex valued function, okay? Which means that the roots of, or the poles of this transfer function can be complex numbers. Okay, and of course, H is called the transfer function. So this one here is the transfer function. Okay. Try to make sure that the resolution is the best, but fortunately, probably if I zoom too much. So if I zoom too much, is it fine or I don't think so. How about this? Is this okay to you guys? Okay. Okay, so 2 more to go. So convolution, transfer function, okay. So, the third way of modeling linear systems is through nth order nth order differential equation. So in this case here, we're talking about y to the power of n, where n here is the nth derivative of y plus a n minus 1, y n minus 1 plus a1 y1 of t, right, is equal to bn u to the nth derivative plus bn minus 1 u n minus 1 of t plus b1 u1 of t plus b0 u of t. Okay, so this is like an nth order differential equation. Of course, we can go easily if you take the Laplace transform of this, and assuming that the initial conditions are 0, you can go to this representation here, right? You can find a representation between y, the output, and input, right? And this is an algebraic equation. This is a differential equation, and this is one of the benefits of using Laplace transform, right? Is to Laplace allows us to go from a differential equation to an algebraic equation, and we all know that finding a solution of a differential equation may not be easy in most cases. Okay.
Quick question: does that
Yeah.
equation include either a constant term or a y0 term?
No, this is not, does not include that. Oh, you mean here? Oh, I'm sorry. Yeah, that's true. So you have, thank you very much. So there is a constant term here, a0 y of t. Thank you. So this is plus. Yes, of course, yes. So you have a constant term here. So this is a general form of nth order differential equation. Okay, the fourth one is n-dimensional state equation. So in this case here, or sometimes we call it state space representation. Right.
Professor, I think in the differential equation, there will be only one constant term. You won't have that y of t.
No, we'll have a, you mean here?
Yeah.
Why?
Like we are just writing a differential equation form. We already have the first order term for y of t. So
What do you mean? So you mean this one here?
yeah.
No, this is this means the first derivative of y. So this is y dot.
Okay, got it. Okay.
Yeah. So this is this is y dot, y double dot.
Definitely.
Yeah. Y, yeah.
Yeah.
So,
Okay. Yeah. Thanks.
No problem. Okay. So so state space representation, x dot, again, it's a differential equation, right? The state space representation is nothing but a differential equation form. However, as you can see right now, the difference between the differential equation representation and state space representation is that the differential equations are decoupled from each other. In each equation, you have only one first order derivative. So x dot is equal to a of t, x of t plus b of t, u of t. All right. And y of t is equal to c of t, x of t plus d of t, u of t. Now, this is what we will focus on in this course most of the time. It's this one here. Okay. Again, it's technically it's a differential equation, right? But the difference between this one and that one is that this one you have a first order, a set of first order decoupled differential equations. That's what will make up the state space representation of the system, right? Of course, here we need to make sure that we track the initial conditions, x at initial condition or initial time. We are going to call it x naught or x0. This is the initial condition. I'm sorry here. All right. And t is larger than or equal to t0, right? And also make sure that you keep track of the dimension of the state. This one could be the dimension of x could be 1 or could be more than 1, right? So it could be 1, and in that case, we call it a scalar system, or could be more than 1. In this case, in the general form, x of t, we are going to call it, belongs to real number with dimension n, okay? So which means that x is an nth or n-dimensional vector. X is a vector, and A, which is a time-varying matrix, right? So we're going to, so this is going to be n by n. Right? So okay, so just to sum up, 4 different ways of representing a linear system. First one is through convolution. Second one is through transfer function. Third one is through nth order differential equation, and the fourth is through state space representation. All right. This form here is the most convenient in terms of designing controllers, in terms of studying the stability of the system, as you will see throughout this course. Any questions so far?
Professor, I have a question. I'm
Yes.
a little unfamiliar with the notation that you're using. Could you explain again what the R is in the
Yes.
last part?
Yes. So this is a conventional way of representing, of defining matrices and vectors. So R refers to real numbers. Okay. So and R to the power of n, it means that we are talking about a vector, a column vector, okay, with a n dimensions. So if n is equal to 2, that means so for example here, for example, if n is equal to 2, let's say, all right, then that means x is equal to x1 and x2. It's a column vector with 2 components, x1 and x2, and each x, each component belongs to real numbers. Okay, it belongs to the real numbers. So again, this belongs to real numbers. And in this case here, and also A, and A is going to be A11, A12, A21, A22, because it's 2 by 2, and each element of the matrix A is also a real number. Okay, belongs to real numbers. Okay, so this is a conventional way. This is how we represent. If you see it like this, it means that we're talking about a vector of n dimension, and this one n by n, which means that we're talking about matrix or a square matrix, right, of this form here. And of course, this could be, it could be n by m or something, you know, it doesn't have to be a square, right? But if we have it like that, it's a matrix. It could be a square or it could be non-square.
Okay, thank you.
Yeah, no problem. Thank you for the question. We are going to use this notation throughout the course. So thank you. Any other question? All right, so this is one of the benefits of me writing. Sometimes I'll take some, it gives you the opportunity to ask questions and follow with me, but we'll see how it goes. All right. All right, so in general, okay, for linear systems, what we have is a relationship between U, the input, and Y, the output, okay? And the link between the Y and U, this is the system. So this is the physical system or the linear system. This is the output and this is the input. I need to emphasize here the fact that Y is a signal. It could be a current, could be a voltage, could be a force, could be a position, displacement, velocity, whatever. U is also the case. U could be a current, voltage, whatever, right? G is the physical system, is the motor, is the car, is the satellite, is the any dynamic system, right? Any dynamic system that changes with time, right? So, and this is also another conventional way of representing systems that we will adopt throughout the course. Whatever inside the box is a physical system, whatever, and the arrows represent signals. Okay, so this is a system, these are signals. Okay, now let's talk about the definition of linearity. What does it mean? What do we mean by linearity, linear system? Anybody? Can anybody tell me what does it mean for the system to be linear?
The frequency of the input and output remains constant.
Okay, that's true. This
It
is,
follows.
but go ahead.
It follows scalar addition and scalar multiplication.
I believe you're dancing around the answer, but yes, but these are properties that are, you're correct. So let me give you a formal definition of linear systems. So definition. A system sometimes we denote it by G from U to Y. Okay, a system G, which relates U to Y, okay, is linear if for all inputs U1 and U2, for any inputs U1 and U2, okay, and all scalars, okay, alpha and beta, okay. So if I have a couple of inputs, any inputs U1 and U2, and any scalars, any constants A and B, okay, then, so I'm going to call it here such that Y1 is equal to G U1 and Y2 is equal to G U2. Okay, so these are the definitions. So here you give U1, to the system G, it gives you Y1. And if you give it U2 to the system G, it gives you Y2, right? So if that's the case, then if G is linear, then the following holds. The following holds. If you multiply Y1 by alpha and add it to, sorry, that's beta, and add, so this is beta, and add it to a product of beta and Y2, okay, that means G of, and this is an operator. So this does not mean G product of, it's G of alpha U1 plus beta U2, okay, which means that if the system is linear, okay, and if I multiply the outputs by scalars, okay, then it holds that the inputs will also be multiplied by scalars. So as a consequence of this linearity definition, okay, consequence of linearity, suppose Y1 is equal to G U1, okay, then if I multiply by Y1 by 2 Y1, that means we're talking about G of 2U1, okay? So what this means is, if I have this, if I give the system U1, it will give me Y1, okay? Let's say I take that Y and I multiply it by 2. Okay, keep it now aside. Then I take I take the u1 multiplied by 2, apply it to the system. It should give me 2y1. Okay, that's the definition of linearity. Also, if I give the system 0, it should give me 0. That's also a result of linearity, right? 0 should give me also g of 0. Okay, these two should be equal to each other. All right. Mind you, these may not hold for nonlinear systems. Okay, these properties may not hold for nonlinear systems, and I say may because linear systems are special case of a nonlinear system. Okay, so speaking of nonlinear systems, so definition: a system, any system that is not linear is called nonlinear. All right, any questions so far? All right, let's continue. Okay. Let's talk about matrices and vectors till the end of the lecture, so as a review. Okay, so for a matrix A belonging to the real numbers n by n, so meaning that the matrix has a dimension n by n, okay, I'm going to talk right now about the eigenvalues of that matrix. The eigenvalue so can anybody tell me what do we mean by eigenvalues and eigenvectors?
Well, an eigenvector is a vector that when input into the system just results in its scaled version of that vector, and the eigenvalue is the amount it's scaled by.
Yes. So the eigenvalues represent the characteristics of the system, and they also, most importantly, or mathematically speaking, eigenvalues and eigenvectors should satisfy the eigenvalue-eigenvector equation, which I'm going to write right now here. So if we denote the eigenvalue as lambda, okay, belonging to the set of complex numbers, okay, gonna write it this way, and eigenvector, sorry, this is V, eigenvector V belonging to the real numbers dimension n, so this is a vector with n dimensional, and also with the note that V is not equal to 0, okay, they satisfy always this eigenvector eigenvalue equation. AV is equal to lambda. Okay, this is a fundamental equation for linear systems. Okay. We call this eigenvector eigenvalue, or eigenvector eigenvalue equation, or eigenvalue eigenvector equation. All right, so as you can see here, AV is equal to lambda V, where V is the eigenvector and lambda is the eigenvalue, and A is what? A is the matrix. A is this matrix here. Okay, A is the matrix. If we want to relate this to systems, A is the system matrix. We call it system matrix. But this is general, in general, any A matrix. Okay. Let's rearrange this. So take this to the other side. So we have AV minus lambda V is equal to 0. Okay. Notice that V is a vector, A is a matrix, and lambda is a scalar. Okay. So I can also write this as AV minus lambda I times lambda, where I is the identity matrix. I'm sorry. It's AV minus, I can multiply the vector, sorry, by identity matrix, IV times lambda is equal to 0. So see what I did here? Because this is a scalar, I can take it to the left or to the right of this term here, because it's a scalar, okay? If it's a vector, I cannot do that. Second, I can also multiply this vector by the identity matrix and nothing will happen because it's the identity matrix. So this is identity matrix. Okay, identity matrix is a matrix, is a diagonal matrix where the diagonal terms are ones and everything else is 0. Okay, so now I can take V as a common factor here. Again, because this is a scalar, I can move it anywhere I want in this term. So I can now take V as a common factor between these two. So I have A minus I lambda times V is equal to 0. Okay, now you can see that V is in the null space of this matrix here. So note that V is in the null space of A minus I lambda. Okay, so null space, which is this space that if you multiply it by this matrix, it will give you 0. Okay, so in other words, V belongs to the null space of A minus I lambda. Okay, so in general, the set of eigen values of A is the spectrum of A defined by so I'm going to denote the eigenvalues of A as the spectrum, and I'm going to denote that as a sigma, okay, of A. So this is sigma. So this is the definition of eigenvalues. The set of eigenvalues of A is the spectrum of A defined by this one here. Okay. So as you can see in this equation here, this V is called the right eigenvector. V is the right eigenvector. There's also what's known as the, because the right eigenvector, because it's multiplied by A from the right. There's also something known as the left eigenvector. For lambda belonging to the sigma of A, okay, there is a left eigen vector W, and the left eigenvector satisfies the following equation. W transpose A, so we're multiplying A from the left, is equal to lambda W transpose, okay? Doesn't matter where you multiply this side, this term, because this lambda is a scalar. What matters is this term here. So this is the left eigenvector equation, and this is the right eigenvector equation. Okay. And this here, this means transpose, vector transpose, okay? So if you transpose a vector, it's a row vector. So this is a column vector, and this is a row vector. It's like this, okay? Now we talk about the characteristic. Polynomial. So the characteristic polynomial is the polynomial that's based on this equation here. The determinant of A minus lambda I is equal to 0. Okay? So for example, if we have A is equal to 1, 2, 0, 4, okay, then the determinant of A minus lambda I is equal to 0 is given by this. The determinant of 1 minus lambda 2 0 4 minus lambda is equal to 0. Okay, so the determinant, you multiply the diagonal terms minus the multiplication of the off diagonal terms. So it's, so which means we're talking about 1 minus lambda times 4 minus lambda is equal to 0. Okay, which means 4 minus 5 lambda plus lambda squared, this is plus, sorry, this is plus lambda square is equal to 0, or lambda square minus 5 lambda plus 4 is equal to 0, which means that lambda is equal to 1 and 4. So as you can see, that's why we are calling it a characteristic equation. This is the characteristic equation here, right? Lambda square minus 5 lambda plus 4 is equal to 0. Why it's a characteristic equation? Because solving this equation gives you directly the eigenvalues of the system or of the matrix, all right? And as you will see later on when we talk about linear time invariant systems, eigenvalues is very important. They tell us whether the system is stable or not, for example. Okay. Okay. So now we talk about something else that we are going to use throughout the course, which is what's known as the Cayley-Hamilton concept or theory. So define P of A or PA of lambda as the characteristic equation based on determinant of A minus lambda I. Okay, so if lambda belongs to the spectrum of A, or if lambda is, in other words, if lambda is an eigenvalue of A, okay, then PA of lambda is equal to 0. Of course, so this is exactly what we said here, which is the definition of the characteristic polynomial. So nothing new here. Okay, what's new is this. Kylie Hamilton says, Kylie Hamilton theorem says that if I have a characteristic polynomial, PA of A is equal to 0. Not if I have. I mean, if you substitute by instead, so look here. If you substitute by lambda in the characteristic equation here, okay, if you substitute by these lambdas, you will get 0. Kylie Hamilton also said that if you substitute by A in the characteristic equation, you will also get 0. What that means is the following. So we know that the characteristic equation PA of lambda is equal to lambda to the power of n plus alpha n minus 1, lambda to the power of n minus 1, plus alpha 1, lambda plus alpha 0, right? This is the characteristic polynomial, right? Kylie Hamilton says that, okay, this will also hold for the A matrix. If you substitute lambda by A, meaning PA of A is equal to A to the power of n plus alpha n minus 1, A to the power of n minus 1 plus alpha 1, A plus alpha 0 times the identity matrix. Okay, so what this means is that the characteristic polynomial, okay, applies or holds for the eigenvalues. Equivalently, it applies to the matrix A, which is the matrix of the system. All right. So yeah, this is very important. And also the difference between this equation and that equation. This equation is a scalar equation. This equation is a matrix equation. Okay, so each term is a matrix. So this is a matrix. That's why we multiply by the identity matrix here. So this is a matrix, 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 matrix. Everything is a matrix. It has a dimension of a matrix. All right. Still have 10 minutes. Any questions so far?
Professor, could you say again what that says right before the Kaylee Hamilton? It says if lambda it belongs to, but I can't quite see what is that a
Yeah.
G?
No, it's actually this is not G. This is sigma. This is how I write sigma. Okay, and let's go back and see what sigma means. Sigma. This is not G. This is sigma. Okay, so this is how I define eigenvalues. The set of eigenvalues of A is the spectrum of A defined by this. Lambda belongs to the spectrum of A. This is how we define mathematically the eigenvalues of A, which they need to satisfy this equation here. Okay, so this is sigma, meaning that if lambda is one of the eigenvalues of A, or if lambda belongs to the spectrum of A, or if lambda belongs to sigma of A, then this follows. Is that clear?
Yes, thank you.
No problem. Okay, any other question? Okay. So examples. Let A be a matrix n by n with eigenvalues lambda 1 up to lambda n. Of course, if the dimension of the matrix is n, or a square matrix n, then we would expect n number of eigenvalues. Okay. So number one, what are the eigenvalues of A inverse. Okay, what are the, so if we know that the eigenvalues of A are lambda 1 up to lambda n, so what are the eigenvalues of A inverse? Of course, here we assume that the inverse exists, A inverse exists. Okay, so let's answer this question here. Okay, knowing the eigenvalues of A, how can we know what are the eigenvalues of A inverse? So before we go through the mathematics, intuitively, can you guess what are the eigenvalues of A inverse if we know the eigenvalues of A? Anybody?
It's going to be 1 by lambda I.
Yeah, exactly. So it's going to be 1 over lambda I, or one over the eigenvalues of A. Yes, this is what we would expect. So let's do it. So we start by what? We start with what we know, and what we know is that these eigenvalues should satisfy the eigenvalue eigenvector equation. So A P is equal to lambda P. Okay, here I'm assuming that I'm calling the eigenvector as P, and this is the right eigenvector. So now if I multiply this equation from the left by A inverse, so A inverse A P is equal to A inverse lambda P, okay? And we know that A inverse times A is equal to what? Is equal to the identity matrix, right? So which is the same as, so this is equal to IP, which is the same as, so this is IP, which is the same as P is equal to A inverse lambda P. Okay. Now, okay, so now I can divide both sides by lambda. So if I do that, then 1 over lambda times P is equal to what? Is equal to A inverse P. And this is exactly the eigenvector, eigenvalue equation I'm looking for A inverse, right? I'm multiplying A inverse from the right by the eigenvector, and again, I have it. So this tells me that, so first of all, let me write this. Of course, here, whenever we divide by something, we have to make sure that that something is not equal to 0. And this is exactly the case, because if we assume that A inverse exists, this implies that the eigenvalues of the matrix A are not 0. Okay, this is one of the properties of matrices. A matrix is invertible, implies that no eigenvalue is equal to 0. Okay. Okay. So note that lambda is not equal to 0. Why? Because A is invertible. Okay, so now then I reach to the conclusion that 1 over lambda, as Amit says, belongs to the spectrum. So this is sigma, spectrum of A inverse, which means that 1 over lambda is one of the, or are the eigenvectors, eigenvalues, I'm sorry. 1 over lambda are the eigenvalues of the matrix A inverse. Okay, let me stop here for today. Okay, is there any question?
Upon observing this, say, eigenvalue stuff, can I say that any matrix can be represented by a group of differential equations?
So we're talking here about square matrices.
Yeah,
So
but there
and
seems to be a kind of correlation between the, say, the matrix, the square matrix, and the differential equation.
so we will later on in the course we will use this Kiley Hamilton, and we will get a differential equation based on that. So as you can see here, the characteristic equation represents the eigenvalues, but also I can represent it through the matrix here. Now, let me understand exactly what you're saying. So what you're so let me go back to the differential equation representation of the system, which is this here. So can you tell me again what you just said?
I was saying, is it possible to represent any matrix with a group of differential equations?
Give me an example. What do you mean by that? So a group of, so for example, so this one here, this one is a vector. X dot is a vector, okay? Can you differentiate, is your question related to the differentiation of a matrix? Can you differentiate a matrix? Is that what you're saying?
Actually, no. I was more curious about the relationship between the matrix and the differential equation, because differential equation also have a characteristic polynomial which can be used for solving, which is useful for solving, and also determine if the system represented by the differential equation is stable or not.
Yes.
And you also said that the matrix eigenvalue will also determine if the system represented by the matrix is stable or not. So I was trying to think of a way to represent, or just like a correlation between the matrix representation and the differential equation representation. I'm not quite sure how the example should pan out, but I was thinking about it.
All right. Okay. So, okay. Let me see if I can answer your question. I may not be able to answer your question, but for example, here, okay, for this differential equation here, okay, this differential equation, it is assumed that y and u are in the vector form, meaning y could be y1, y2, y3, y4, and u could be y1, y2, y3, y4, and so on. Okay, so this equation, for example, okay, is applicable to both cases when y is a scalar. There is only one y and one u, but also is applicable when you have different y's and different u's. Now, now you could have a case where W is equal to W1, W2, W3, W4, okay? And W dot is equal to W1 dot, W2 dot, W3 dot, W4 dot, okay? Now, can this satisfy an equation of this form? Maybe, I don't know, okay? But this equation here, this we mean, and the same as this equation here, okay? So this equation here, x dot, let's take this equation here. This means x1 dot, x2 dot, okay? But let's take the example when n is equal to 2, okay? So, and by the way, a vector is a special case of a matrix. A vector is a special case of a matrix. So theoretically speaking, whatever is valid for a vector form should be valid for a matrix form. You just need to pay attention to the dimensions. But this one could be an example of A11, A12, A21, A22 times x1, x2, right? Plus B1, B2 times u could be 1, could be 2, right? Could be a scalar, but also it could be, yeah, it's a scalar. So let's take it as a scalar, as just u1. like that. Okay, so it's a scalar. So I'm not sure how to go further beyond this point, but maybe we can discuss it later regarding your question.
Or maybe I just try to find a, say, a n=2 example myself. Probably I'll pan it out. Or
Yeah,
just a
exactly.
spring mass dampening system like that. I'll probably just pan it out myself.
Right. Okay.
All right.
Sounds good. Final note about this. Maybe we'll have a chance to talk about Riccati equation. Riccati equation, which are a solution of typically Kalman filter. Okay. They, for linear time varying systems, they took, I think we'll talk about it in this course. P dot is equal to AP plus P L transpose plus, I believe, Q plus something else. Anyway, okay, this P is a matrix, is not a vector. Okay, and later on, you can treat this in the same way as you treat this and that one, and you can find a solution for this equation here. Anyway, this is off topic for now. Thank you very much, all of you guys, and see you on Thursday. Please, I'm going to post this online. You can look at it. Please read chapter 1 and chapter 2 of Rogue's book, okay? And read the material that are posted online. Thank you very much. See you on Thursday. Bye-bye.